Hello everyone! Welcome to the Deep Instinct demonstration. I will start by explaining the differences between machine learning and deep learning, followed by a short overview of the architecture of the Deep Instinct security platform. And then, of course, the demonstration. Machine learning doesn't look at all of the data, but only a subset of the data. In addition, it requires a human domain expert to define and engineer features to perform classification. This results in an accuracy of only 50 to 70% and a false positive rate between 1 and 2%. Deep learning features a deep neural network. Think about a human brain, which has a unique capability to solve tasks that machine learning models cannot. With deep learning, all of the data is looked at, so 100%, and no subset of the data. This results in a high accuracy of more than 99% and a false positive rate of less than 0.1%. And perhaps best of all, there is no feature engineering, so it's much more difficult for adversaries to understand how we work with deep learning. And by deploying a prevention-first strategy, we prevent the execution of known, unknown, zero-day and APT threats before they could cause damage to your endpoints. And that without using signatures or heuristics. Now let me explain the architecture of Deep Instinct. In the Deep Instinct labs, we have trained our deep neural network with third-party public sources, homemade malware and mutated malware. And the result of this is the so-called D-Brain. It only gets an update twice or 3 times a year, and the version of the D-Brain is then being deployed. These updates are sent to those D appliances for this deployment, the cloud-based management consoles of our customers and partners. D clients are then installed on the endpoints, such as mobile devices, laptops, desktops, servers or virtual environments. The lightweight agent containing all of the technology for the best prevention. For environments where no agents can be installed, or where it's not desirable, we have a prediction platform for cloud, web gateways and applications. Now it's time for the actual demo. And if all works well, you will see my desktop right now. What we will be showing in this demo is how Deep Instinct gets multiple swings at the same pitch. Our layered prevention strategy in the same agent means that we will prevent the attack before it gets an opportunity to encrypt or exfiltrate your data. I'm going through a number of Deep Instinct's agent's capabilities. Not all of them, but just a few. And as you can see, I have installed the latest production version of Deep Instinct on my endpoint. By the timing of this demo, it is 3.1. And what I'm going to do is run through a number of scenarios. I'm going to take a look at downloading unknown PE files, unknown doc files, unknown PDF files. But also going to take a look at a couple of fileless examples. And at the end, of course, look at an event within our management console. So to start, I'm going to go pull this folder on my desktop as you've seen and run the script to download these 25 PE files. I don't know what these files are. They're going to be chosen at random from a public malware repository site. That site is not owned by Deep Instinct, so it's true, the files are live pieces of malware. They're confirmed malware and completely unknown to myself. We are pulling these samples which are just from the latest few hours. And the artificial brain that is going to be examining these files is right now a couple of months old. And the samples are going to be brand new to the artificial brain as well. So, statistically, it has never seen these files before. The first script I'm going to launch is the PE downloader. And what this script will be doing is just kick off a Python script with my API key to download those samples from this malware repository site. Going to download 25 samples. And as you will see, as these files are beginning to write to disk, the artificial brain is coming into action. And you can see how fast it is processing these samples. We can see in the pop-up we're dealing with several different types of threats. And the artificial brain is going to classify these threats for you, whether it is as a worm or spyware or ransomware or what have you. The samples that we've shown you now are the so-called PE files, the portable executable files. And we know that some ransomware attacks started with the download of a PE file. But not all attacks use these types of files. Let's run the second script, which will download 10 PDF samples. Again, I want to stress out that we don't know what these PDF files are. Unknown to us, coming from a public malware repository site. We are determining that these PDF files are malicious, and we do that pre-execution. As the bits are writing to disk, the artificial brain is able to determine that these files are indeed malicious. So why is it important in this scenario to do PDF files pre-execution in prevention? Pretty simple. PDF files, but also doc files and even Excel files. They are the most common form of infiltration. Why? They're being emailed to an HR department, legal department, perhaps shipping departments, or accounting departments. It is the literal job of these employees to open up these files so they can get their work orders, shipping instructions, or in the case of HR, they often receive PDF or doc files from web-based email accounts from people that are sending in their resumes. So it is very important that you have a tool that is able to identify these threats pre-execution. Because what happens if you wait for this thing to run? If a human double clicks on it, it becomes a race condition. And who can do it faster? Can the encryption do its job faster? Can the infection happen? Or can the data exfiltration happen? Or even your detection and response tool, is it fast enough? With the pre-execution model of Deep Instinct, none of that becomes a consideration. The deep learning model is always going to win. Now let's see how it handles unknown doc files. We're going to do 10 more random samples. Once again, the downloads are coming from a public malware repository site. This is the power that deep learning with Deep Instinct can do. Not based on signatures or heuristic models, or even machine learning feature extraction. And this is what the artificial brain is doing in sub 20 milliseconds or less, which is 5 times faster than the average blink of a human eye. I've shown you now some scripts that downloaded files. Let's show a more real-life scenario in which we have Outlook with several emails. In the first email, we see an email with looks like to come from a finance department with my payslip for the month of June. As all looks pretty legitimate to me and pretty normal, what would the user do? Just open up this file. When I open up this attachment, what we can see is the artificial brain was able to attack pre-execution. Prevent, of course, this attack pre-execution before the application Adobe Reader even was fully opened. Let's look at another email example. Again, coming from the finance department. Still, it looks normal to me asking to look at this offer and approve this offer as well. Let's do the same. Let's open up this email with the attachment and see what happens. Again, we can see that Deep Instinct was capable of preventing this attack pre-execution immediately, even again before the application Excel was fully opened. Now let's go into my last email example. An email that looks like to come from a LinkedIn member asking to invite for him his acceptance of his invitation. From the moment I click on this link, the LinkedIn page will show up asking me to log in with my credentials. But before I do so, I see a pop-up message asking me to install a plugin, which apparently is required at this time. Not aware of any risks, users just like to follow the prompts and click on this notification bar as well. What happens, and luckily I have Deep Instinct installed on my endpoint, is that it prevented the download and execution. As we can see in the browser, the download was errored out, the download of a ransomware file on my end system. But what if? So far I've not shown anything but files. What happens if we're going to miss something? Surely we cannot be selling a silver bullet, and we're not. No cybersecurity company is. And that is really the point of the demo. A point of the demo is, what happens if? What happens if a threat would be able to pass the artificial brain? And let's take a look at some of these scenarios. What if a sample got through the artificial brain and launched a PowerShell attack? Here I have a batch file. And all that this batch file is going to do is open up a PowerShell command prompt. And the script will then run a file from PowerShell's page on GitHub and perform some actions. Now let's run this file as an administrator on my endpoint and see what happens. As you can see, we are using a bypass command. And you can see we have yet another engine coming into play. The behavioral analysis with malicious PowerShell command execution. This is a good example of a fileless attack. It's just a human being that is able to deliver a command and has nothing to do with a binary. While it did launch from my batch file, all it was doing was open up a command exe and typed in that PowerShell command. The script attempted to invoke Mimikatz and dump our credentials. The so-called credential dumping attack. Although this is still a binary-based attack, of course, it never got that far. The malicious PowerShell model we have is the world's first and only deep learning model trained on malicious PowerShell. And you can enable, of course, the content in your organization for PowerShell while still being protected. PowerShell has been a double-edged sword for many years. It has been super helpful for so many organizations, but at the same time, it's an incredible attack vector. With Deep Instinct, we have the ability to protect against that. But what if? What if a malicious actor just had root access and tried to perform credential dumping directly using a proc dump of LSAS? Now let's run this script as administrator and see what happens. A whole new model is coming up, and this time it is the credential dumping model has been engaged. You may have noticed that it was not launched by binary, so the artificial brain didn't pop up. We also did not launch it with PowerShell, so also our PowerShell models didn't pop up. How about a malicious HTML browser extension attack in order to prepare a browser for compromise and possibly be used to begin a dropper phase? Here I have an HTML injection, and this can really commonly occur, like you're browsing the web and come across an infected site. Let's see what happens when the injection begins to do its job. Right now, our HTML model popped up and our script control was able to stop the threat as well. Here we've just seen a couple of examples, right? We looked at the pre-execution with portable executable files, PDF files, document files. We also took a look at PowerShell and straight credential dumping. And lastly, HTA injections. At this moment in time, the endpoint was online with an active internet connection. The good thing about the artificial brain is that it only gets updates twice a year. It doesn't need an active internet connection, nor it uses signatures. So let's have a look at how good and fast the prevention is when we download 40 samples and then disconnect the internet connection. Again, when I will be downloading files, they will be randomly chosen from a public malware repository site. That site is not owned by Deep Instinct, so yes, it's true, it's live pieces of malware, and they're confirmed malware and completely unknown to myself or the brain. Pulling these samples from the last few hours. The artificial brain that's going to be examining these files right now, a couple of months old. And the samples are going to be brand new to the brain. Statistically, it has never seen those files before. So while those 40 samples are now being downloaded and stored in an encrypted zip file, let's disconnect the network adapter when it happens and when it's finished. So we have seen the files are being downloaded. I have the zip file here. Now let's just disconnect the network adapter of this device. Let's confirm this by seeing if I have an active internet connection. If I'm able to read CNN.com, for instance. no internet connection. Also make sure that the artificial brain and our agent are indeed offline. Here we are. So let's unzip this encrypted zip file, and for the best view, let's encrypt those on my desktop. I will put in the password, and then before I click the OK button, let's see how fast it is while it tries to save those files to disk. Of course, none of this was capable of happening. We can see that the artificial brain is able to pick this up pre-execution, meaning our agent is as good online as it is offline. And this can of course be of major benefit for many organizations where endpoints aren't always connected via internet, but for instance do use other means of file sharing. Now let me show you a piece of live ransomware. Let's see what happens if malware was able to bypass the artificial brain and was able to execute. Can we stop it before the encryption phase? Of course we can, with an arbitrary shellcode engine. But besides that, I really like to show an example of a well-known ransomware called DarkSide 2.0. DarkSide 2.0 was a ransomware first detected in August of 2020, but it came back massively in 2021. Think about the Colonial Pipeline attack. DarkSide is capable of starting the encryption of endpoints within seconds. It can use up to 32 CPU threads per second. And this causes, of course, that it destroys the race condition I mentioned earlier. There is no detection and response system that is fast enough. Which means they have to rely on signature-based systems that are trying to catch something like this. Now let's run this file and see what happens. First, you can see it starts to save some files on disk, and then we see a malicious PowerShell command execution. The first thing it tried to do to compromise this machine. But it didn't work. Our model popped right up and prevented this from happening. But you can also see the second step of this attack, and which is the ransomware behavior, the actual phase where DarkSide tried to execute and encrypt data on our endpoint. And of course, it was unable to do so. You can see that we stopped that behavior with our ransomware model. DarkSide is encrypting in seconds, but we are preventing in milliseconds. So our models are faster. Of course, we also do have a robust management console. I'm going to just show a little part of it, a single event. I really like this example, but before I do, of course, I could also inform you about our multi-tier, multi-tenant environment. But of course, we can show you all of that during a proof of value. The reason I'm showing you this PUA, the so-called potentially unwanted application, is because they're often ignored by organizations. Most SOC personnel and security analysts dismiss them as low priority or low threat alerts. But take a look at this one. While classified overall as a PUA for 78%, it also contains a virus, spyware, dropper, backdoor and 1% ransomware. 1% ransomware is 100% bad, and it can of course encrypt your machine. This kind of obfuscation is common because threat actors know that if they can get their attack classified as a low priority alert, they have a better chance of getting into the environment. But as I've shown you, this is ransomware. And remember, 1% ransomware is 100% bad. But with deep learning and Deep Instinct's artificial brain, you don't have to worry about these types of threats or tricks by malicious actors. This was the actual demo. So recapping, Deep Instinct offers the best prevention, pre-execution based on deep learning. So what are the benefits of using deep learning? No signatures, no machine learning feature extraction, no need for heuristics or sandboxing, and endpoints don't need an online requirement, and of course, no need for file execution. Thanks again for viewing the Deep Instinct demo, and we would love to even show you more during a proof of value.